guys. I hope that you guys are having a great day. Today, I'm looking at my window in front of me. It is a really blustery and cold day. Got a ton of snow happening out there in my garden. So I'm hoping that when this video reaches you, it is going to be a nice and warm day. And that after you do this lesson, you will be able to get outside and enjoy the day. I sure do miss all of you guys, and I'm looking forward to spending a little bit of time with you. Don't forget that all of us teachers have office hours and that they're all posted for you guys. If you have any questions, email us on that. I do think that to get the most out of this particular video, you need a periodic table to help yourself out. And the other thing is you can either print this page and it should be attached to the assignment, or you can just use loose leaf paper. Don't forget that you can pause yourself, pause this video and kind of catch up. So that's one of the benefits of having our time together on video. So before I get started, I want to just give you a little bit of big picture about where we're headed. So on April 16th, we did a polarity exploration, and that was a tough lesson for a lot of folks. It was an introduction to polarity, which is a major theme in covalent compounds. And so it's really just an introduction. I want to promise you guys that we're going to loop back around to that. So we start with polarity, and then we are introducing you. I think you were with Miss Olson on Tuesday, and she showed you how to do the have, want, need, bond method and such. And today I am going to introduce molecular geometry, which will help us refine our Lewis structures and our models. And then eventually in the next couple of sessions, we're going to teach you how to apply polarity overall to molecules. This will lead us to a huge topic called intermolecular forces of attraction. Sounds scary, but it's not too bad. But it is a very important topic because it explains things as to why the two helices in your DNA actually stay bonded together. It explains why paint stays on the walls, why some organisms can stick to the side of a wall. So there's a ton of application to it. And so that is what we are building toward. So I'm going to go ahead and get started on our lesson. I'm going to do a very quick recap. Sometimes it's good to hear something in a different way. And so I hope this is going to help you today. So I'm going to get my glasses on here. You'll probably see my head down for quite a bit, but here we go. So we've got our molecular geometry guided notes. I want to remind you that the word molecular means covalent. And specifically, we're talking about covalent compounds. And these are specifically when we have a nonmetal. Whoops, there's an N that goes there. That is attracted to another nonmetal. I like to put a little heart there. And they do this by sharing electrons. Okay. So quick recap here. Over in this section, I think I'll just use my highlighter. We've got our metalloids here. So we're talking about this region of the periodic table over here, plus our hydrogen for our nonmetals. Can you hear my dog barking back there? It's like he knows that we're recording a video. It's cracking me up. Okay, so nonmetals attracted to nonmetals. So you're dealing with elements over here. So when you met with Miss Olson last time, she talked to you about naming. Just a reminder that you use prefixes. When you see the prefixes that are like mono, di, tri, tetra, you know that you have most likely a covalent compound. And so that's a big clue. When you have an ionic compound, you are not going to see these prefixes. Okay, so this is important. Okay, she introduced the have, want, need, bond method. And so I want to remind you that have is the number of electrons. I'm going to use E minus for electron. Oh, I'm noticing that we're going out of focus. Let me see if I can get that to focus for us. There we go. Okay, so Okay, so sorry, my dog interrupted me, or I'm getting back to the have. So when we look at the have, that's the number of electrons, E minus. The molecule, the covalent molecule, actually has. Okay. Now what's really important about this is there will never be any more electrons in this. So these are the electrons that the molecule has to work with. The want, on the other hand, is the number of electrons the molecule wants, but will never have. It actually can't have that number of electrons. So that brings us to the need. Okay, so the need is the number of electrons that need to be shared. And Miss Olson told you that if you take the want minus the have, you get the need. Okay? Now to get the number of bonds, you're going to take the need and divide it by 2, because every bond has 2 electrons. And this will equal the number of bonds in the molecule. Okay? So what we're going to do with this information is create a Lewis structure, which you have begun already. It's a basic drawing of a molecule. And it includes bonds, atoms, lone pairs. And it shows the connections and eventually the shape. And that's what I need to key you in on today. So we're going to start looking at 6 common shapes, 6 common molecular shapes. There are way more than this, but we're going to only work with the 6 common. We call them the simple shapes. And when you hear that word molecular shape or that phrase molecular shape, you'll sometimes hear people refer to this as the molecular geometry. Now, with molecular geometry, I cannot underscore the importance of the central atom. The central atom determines the overall shape. That's important. So it tells us the overall shape and how the legs, which are really the atoms that are attached, and how the legs are angled. Okay. So in order to have a central atom, I am going to point out this. You have to have 3 points. So this goes back to your math class. So if we have 1 point and we have another point attached to it, there really isn't an angle. We actually have to have a third point, and that's, so those 3 points, and here we call it the vertex in math, and in chemistry we'll call this the central atom. And in chemistry and in geometry, you can actually figure out what the angle, like how many degrees that angle is, like with a protractor, or you might use some type of mathematical computation, so sine, cosine, etc. So that's important. Now, in order to identify the central atom, first of all, my first thought is always this. The central atom has greater than 1 bonding area. Okay? It has to have more than 1 bonding area. So even if I look at this picture right here, if this is a central atom, it'd have 1, 2 bonding areas. If I cover that up and I only have the 1 bonding area, I really don't have a place for an entire angle, and therefore I don't have anything that's central. Okay, this obviously the vertex is in the center. Since that's true, a little subpoint of that is that hydrogen and all the halogens, so halogens are group 17, that include things like fluorine, chlorine, bromine, iodine, etc., can only form 1 bond and are, and I'll make this big, never central atoms. So they will never, ever, 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 ever be central atoms. Okay, so that's an important point. Okay, the second thing in identifying the central atom is this. It's often, like I'll say 90-ish%, often the first element listed in the formula. Unless, of course, it's hydrogen or fluorine, chlorine, bromine, or iodine. Okay, so I will tell you this. These 4 here are very, I don't know if I can think of a single situation where I've ever seen those halogens listed first, but you will see hydrogen listed first, and you know you just skip over it. It is not going to be your central atom. So again, it's often the first element listed in a formula. So if I had CH4, the central atom would be carbon. Okay, let's keep moving on. I'm going to go to my next page. And what I'm going to do now is introduce you to the 6 basic shapes. When I teach them to my students, I like to put it in a 3x3 grid. Helps me organize my thoughts, and you're going to see that you can draw some connections together on these. So again, we're going to see these, and then I will show you how to apply this information for you. Okay, so the first thing I'm going to mention is electrons come in pairs. Okay, and when they're in those pairs, the pairs repel each other because all the pairs are negatively charged. With that in mind, that means that they are going to spread out. And that is at the heart of why or what the shapes end up looking like. Okay, so looking at our first shape, you're going to see I'm always going to start with my central atom. And so I'm going to first draw a little central atom here. And let me actually show it to you. I brought home some models. So this is our first shape that we're going to look at. And it's 3-dimensional. And so right now I'm drawing this black atom right here. Let's just say it's carbon, for instance. And here's my carbon. So the next thing I'm going to see is that coming straight out of this molecule, we're going to have another attachment up here. Then there's going to be an attachment to the left and an attachment to the right. So one to the left and one to the right. Now both of these attachments are coming out towards us. Okay, so they're coming out literally in space towards us. And then you're going to see if I tip the molecule just ever so slightly, there is one attachment that is actually going back into my desk. And so we draw that here, and we draw the line slightly shorter, and it makes it look as if it is going back into the desk. Now, I am not a fantastic artist, but I will tell you this. I think that all of you can draw these types of this stick and ball and stick diagrams. Use these as references for yourself. I will also post a nice typed reference for you guys. Okay, so in this one, I want you to notice there's the central atom. I'm going to keep this out here so you can see this. And then we've got our 4, let's say, hydrogens attached. And so there's 4 things attached, and we call this a tetra, which stands for 4-hedral. So that's the molecular shape name for this. Notice how all of these molecules are as spread out. I'm sorry, not molecules. All of these atoms are spread out as far as possible. Okay, so they have maximized the distance that they can be from each other. So they're trying to spread out. So this pair of electrons, this pair, and this pair. I should mention that each one of these lines represents a bond, and for every bond, there are 2 electrons. Okay, so there's a pair here, a pair here. So a bond is 2 electrons or an electron pair. Okay, and all those pairs are trying to spread out. Now, we mentioned earlier with the geometry that there would be a certain angle. The angle for tetrahedral is 109.5 degrees. This is the average for most molecules that are in the tetrahedral shape. That means there's 109 from here to here. So here's the 3 points, 1, 2, this is the central and the third. And then we've got 109 here, 109 here, 109.5 here. So 109.5, 109.5, 109.5. I turn it, 109.5. All of the angles associated with this, where I can find 3 points, are going to have 109.5 degrees. Okay? Now, our next shape, I'm going to take my tetrahedral, and in the next box, I'm going to modify it just ever so slightly. So I'm going to remove the top portion of this. So this has come off, okay, and I no longer have a bond to this. And I'm going to redraw this, but in my next box. And so I've got the central atom there, right here. It's shown in black. I've got the one going off to the side to the left. I've got one off going to the side to the right. And then I can say that I've got one going back towards the board, or if you want to change it, you could have it coming out towards you. It's easier to draw behind, okay? But we know, according to the octet rule, that this needs to have 8 electrons. And so there's 2, 4, 6. So our 7th and 8th electron, or our final electron pair, is going to be up here, and we call this a lone pair. Now, lone pairs take up a lot of space, okay? And these lone pairs push the bonded pairs even closer together. So our bond angle for this is going to be smaller than 109.5. It goes down to 106.5. Now, we also have to give this one a name. This has 1, 2, 3 things attached to it. So the first part of the name is called trigonal for the 3 attached. And if you look at this, it's got a pyramidal shape. Okay, if I put this down flat on my desk, I can actually get my finger underneath here. And so you'll see that it's actually a pyramid. So this is trigonal pyramidal. Okay. Now, one of the things that we want to record as we go here is how many bonding areas and how many lone pairs there are. This is going to help us very quickly identify what kind of shape we have with our different examples here. So here with the central atom, I've got 1, 2, 3, 4 bonding areas. So I'll say 4B, and there are no lone pairs on the central, so I'm going to say 0 lone pairs. On the central atom here, I've got 1, 2, and 3 bonding areas, and there is 1 lone pair. Okay, let's move on to the next one. And so on the next one, I'm going to just remove one more of these. And now I have this shape here. Okay, and this is a very famous shape. Water takes on this shape. And so let's go ahead and draw this. I've got my central atom here. Off to the left, I've got one, and off to the right, I've got one. And I have nothing else attached. So you see that center, that piece going to the back is gone. Now, this molecule here still needs to have 8 to satisfy the octet. So 2, 4, then I'm going to have 6, 8. And so these take up a lot of space here, these lone pairs at the top, and they're going to push these even closer together. So I probably should have drawn that even closer together. So the bond angle here is 104.5 degrees. So maybe I should draw it like this. These really, so you can see that's getting close together. Here's 1, 2, 3, our 3 points there. And you'll see that we like to call this bent. And to clarify, since there are actually going to be two bent shapes, we see that there are two lone pairs here, so often we'll put a 2 in parentheses. So let's mark before we go on how many bonding areas. The central atom has 1, 2 bonding areas, and it's got 2 lone pairs. So that's my first row, and now I'm going to go on to my second row. My second row, I'm going to start with a new little molecule. And that is this. Okay. Now you'll see that this has something different on it. It actually has a double bond on it, but it has a shape unlike anything else here. So this does have 3 attachments, but it's got a double bond, which is not in this shape here, the trigonal pyramidal. So let's look at what's going on in here. So in this one, we've got maybe our carbon, or it doesn't really matter which atom is here. So we've got a central atom here. I know it's central because it's got more than one bonding area. And then I think I'm going to flip it and draw it this way. Doesn't really matter. I'm going to draw the double bond here. That's down to that red atom. Here's one, and here is one right here. Okay. So in this one, you're going to notice there is always a double bond. You won't have this molecular geometry without a double bond. So this central atom has 1, 2, 3 atoms attached. So it is also going to be called trigonal. But instead of being a pyramid, do you see that this actually lays flat? I cannot get my finger underneath this. So we call this trigonal planar. To me, it looks a bit like an airplane propeller on the front of an old airplane. And so, or a peace sign. So if I put a circle around it, it's got like the peace sign. And so it's kind of a perfect circle divided into 3, which gives us 120 degrees. So the number of bonding areas is 1, 2, and 3. So there's 3 bonds. And there are 0 lone pairs because this atom here has 2, 4, 6, and 8 electrons around it. Just keep in mind that you have a double bond in this one. All right, so just like I did with the others, I can take this molecule and I'm going to take the top off of this one, if I can get it apart. And now I'm going to go on to my next shape. So you can see that this shape is similar to the bent, but it has a double bond. Okay, so I'm going to remove this here. So now I've got this, and then I've got my double bond, and I have a single bond. All right, I'm going to pause because I've got a dog talking to me right now. Okay, so we've got the double bond here, we've got the single bond here, but this atom in the center needs to have its 8 valence electrons to fulfill the octet here. Remember, the octet came about because it's got 2 electrons in the s orbital and 6 electrons in the p orbital. So 2, 4, 6, and then I've got 1 set up here, and again, it takes up a lot of space, pushing these 2 closer together. So it's got to be an angle less than 120. We've got 118 degrees. Again, these are averages. So if you look up a specific molecule, you're going to find that it's somewhere around there. So this 2 is also called bent. But instead of being a bent 2 with 2 lone pairs, it only has 1. Okay, everybody, I gave the dog a toy. Let's see if that keeps him satisfied for a while. So again, the bent 1, meaning it has 1 lone pair. It's got this double bond and a single bond. So 1, 2 bonding areas, although there are technically 3 bonds, right? 1, 2, 3. And our angle is going to be smaller than our trigonal planar because the lone pair is pushing these pairs even closer together. We've got 118 degrees. Our final shape is linear. Okay, and you can imagine with a linear, we've got 180 degrees, and there are two different situations with linear. So I'm going to draw a central atom up here, and with the linear, what we can have is we can have a double bond to the left and a double bond to the right. Now, honestly, I forgot my extra double bonds, so you'd have to imagine a double bond over here, but if you notice right down here in my example, do you see this double bond and this double bond? And do you see how it's quite linear? So this is one situation. The other situation that you can have is you can have a triple bond, 1, 2, 3, and a single bond. Often it's like a hydrogen on this side, or it could be a halogen, and we get 180. So from here to here is 180. Okay, so that's our linear. Now I noticed I forgot to put the bonds and the lone pairs over here. So 1, 2, 2 bonding areas, and 1 lone pair here. And then on our linear, we have 1, 2 bonding areas, 1, 2 bonding areas, and 0 lone pairs because 2, 4, 6, 8, or 2, 4, 6, 8, the octet is satisfied there. Okay, this is where I think you should take a little break, and I think you should come back in a couple of minutes, get yourself a snack, have a drink, do something to get yourself kind of refreshed for a few minutes, and then I'm going to go through a few examples for those of you who want to see how we can apply this. Okay, I hope that you had a good little break there, got a snack. I'm going to go over 4 different examples. Pick these examples very purposefully. They are going to help you get yourselves ready for the assignment Molecule Lab B. Molecule Lab B is a little bit more challenging than the last one that you did. I am going to have a separate video that is going to kind of go over some of the instructions for that particular lab. And so keep your eyes peeled out for that as well. Okay, so here we go. I have a sample here. It's, I believe, the same example that I put in Molecule Lab B. So I'm going to leave that be. I will say I think this got cut off a little bit, so I'm going to make those a little bit more clear. But just to go back at, if you need a reference, this is a good spot to look. So I'm going to go ahead, and one of the things that I recommend when you do this is, since this is the exact same setup for the lab, is I like to go first through and identify my central atoms in all of my examples. So I'm going to do that first. So carbon here, again, carbon because it's the first atom there. Here, hydrogen is listed first, so I know that can't be the central, so I just go to the next one. For my other 3 examples, I've got sulfur, carbon, and then interestingly, in this example, I have 3 carbons. And so there's going to be 3 different situations with that. I'll get to that later. So I'm going to come back here. I now have the central atom chosen for each one of these. For the next column, I'm going to put the name of each one of these. I like to do all this stuff first, and then I can really concentrate on the shapes and the Lewis structures. So for this one, there's 2 different ways that you can name this. So this is dihydrogen monoxide. And then it also has the common name of water. Okay, so that's one of them. For my next one, I've got sulfur. Notice it's not monosulfur, but just sulfur. You never start the name with mono, so sulfur dioxide. Next one is a famous molecule, carbon monoxide. Second word can be monoxide. And then this one is actually what we call an organic or a hydrocarbon. And so I'm going to show you how to do the regular name. So we'll say tricarbon tetrahydride. But this is not what people call it. Okay, so it's better known as propyne. We will teach you later on how to do this. It's not necessary for what we're doing today to know how to do this. And so just don't worry about that name yet. We'll get there. Okay, now I'm going to come back over here, and now I'm going to work across in rows. So one of the things that I have found helpful is to get the have. I like to just put a little H here, and I like to put a little W here for want, and I work above and below. So the have is going to be found on the periodic table. So have is for hydrogen is in column 1, so it's 1, but I have 2 of those. So I'm going to say I have a total of 2 for the hydrogen. And oxygen is going to have 6 valence shell electrons, and there's only 1 of those. So 2 plus 6 gives me 8 for my have. Okay, that's all I'll ever have in terms of electrons, or all water will ever have in terms of valence electrons. Hydrogen wants 2, but there are 2 of them, so it wants a total of 4, plus oxygen, and really just about everything else wants 8. So 4 plus 8, and that gives me 12. The need will be 12 minus 8, and we get 4 electrons that need to be shared. Each sharing or bond has 2 electrons in it, so 4 divided by 2 is 2. So in this situation, we're going to end up with 2 bonds. So now I know my central atom. I'm going to put it in the center. I'm going to attach with a single bond a hydrogen to each one of those, and that gets me my total of 2 bonds. So I really don't need to put any more bonds in. Hydrogen can only have 1 bond. And then I'm going to add on here the lone pairs. So 2, 4, here's number 5, 6, 7, 8. It takes up a big amount of space, so pushes those in. So I see I've got 2 bonds and 2 lone pairs. Okay, so I sort of drew this one already in its shape. You may have drawn it straight across, and that's fine for a Lewis structure, but when we get to our final structure, we want to use the shapes that are up here. And honestly, as you practice these, you'll start seeing which ones you need to draw them as ahead of time. But it just takes practice. And so if we look at this right here, I'm going to fold my paper, I think. It looks, I think I can do this, folks. It looks a lot like this one. 2 bonds, 2 lone pairs, and so I definitely have a bent with 2 lone pairs. So I'll end up being able to draw this using my shapes here. Now I'm going to recommend that you go to the 3D simulation to best do this, but it's nice to see if you can get it on your own. So this is going to be my oxygen here, okay? And then it's going to be my hydrogen here, my hydrogen here. Now, that looks like this. And I'm telling you, there are 2 lone pairs up here. So some people like to draw the lone pairs in. It's not required in the final model. But I do want you to put the bond angle. And so from here to here, whoops, maybe I'll just do 1 arrow. From here to here, the bond angle is going to be 104.5. And I'm just looking up here at my reference chart that bent to is around 104.5. Okay, let's go on to our next example. Okay, so with our next example, we've got sulfur dioxide. And so let's do our have. I like to do the have on the top, the 1 on the bottom. So I've got 6. 6 times 2. Again, I'm getting that 6 from the periodic table. That's the number of valence shell electrons. And that's 12. So 6 plus 12 is 18. Sulfur wants 8. 8 times 2 is 16. So really 3 that need 8. So that's 24. 24 minus 18 is 6. divide that 6 by 2 because there's 2 electrons per bond, and we get 3 bonds. I've already circled my central atoms, so I'm going to write sulfur in the center here. Okay, now I'm going to do this like I see a lot of students do this, without the shape at all here, and then we'll draw the final shape here in our 3D model. So I've got my sulfur here. I've got 2 oxygens. A common mistake is for students to draw on 3 oxygens. There are not 3 oxygens. There are only 2 according to the formula. I'm going to try to focus this again. How are we doing there? Is that better? Okay, good. And so I'm going to put 1 oxygen here and 1 oxygen here. But this says we need 3 bonds. So one of these is going to be a double bond. I'll do this one off to the side. I could have equally done the one off to this side. So now I've got the number of bonds taken care of. I'm going to put my lone pairs in. So this has 2 for this oxygen. There's 2 here. So I need 3, 4, 5, 6, 7, 8. Again, those electrons are going to come in pairs. For the sulfur, I've got 2, 4, 6. So there's going to be a pair here, 7 and 8. For this oxygen, I've got 2, 4. So it needs 5, 6, 7, 8 to bring it up to that 8. Now, in order to figure out the shape, we look at the central atom. Again, it's always examining the central atom in order to get the shape. So in this one, we've got 1 bonding area and another bonding area. So there are 2 bonding areas, and there is 1 lone pair. That lone pair is going to push these downward. Okay, so what shape do we think it is? It's bent with 1 lone pair. Now listen, you don't have to have this memorized. What I would do is just keep looking back at my reference sheet. So here on my reference sheet, this is the only combination where I have 2 bonds and 1 lone pair, and you can see the bond angle of 118. So when I finally draw this out, I've got my sulfur here, I've got my oxygen, whoops, I'll make that a double bond here, and I've got another oxygen here, and the bond angle is 118 degrees. Is that making sense? I might even write bent 1 again, just because then I can really visualize what bent 1 looks like. Okay, 2 more of these, and then we will be done with this. So I thought I would do one where I only have 2 atoms. And so let's just do this one together. Carbon, group 14, we've got valence of 4. Oxygen has a valence of 6. And that gives us a total of 10. And then 8 is what this wants, and 8 is what this wants. So that's 16 electrons that it wishes that it had. 16 minus 10 is 6, divided by 2 gives us 3 bonds. Now, folks, that's interesting. We have got to do 3 bonds with 2 atoms. Now, is this really a central atom? Not really. Why? There's only one thing attached to it. So I'm going to do C and O. Notice that I can't really draw anything exactly in the center here. So we usually start off with a single bond. There's nothing else to bond to. So we've got to get 3. So 1, 2, 3. That's a beautiful triple bond. And now with that triple bond, I still have to check to make sure that they all have 8 electrons. So this carbon has 2, 4, 6. So here's 7 and 8. And this oxygen has 2, 4, 6. So here's its 7 and 8. So what's its shape? Well, really, there's no shape or no geometry because there's no third component to it. There's not a vertex. Some students will list this as linear, and I would say it's linear sort of. Mathematically speaking, we don't have a true angle here. So I think that's kind of interesting. But you're going to see, hey, it does spread out, and we're going to be able to make this like this. Here's an oxygen, and we've got a nice triple bond connecting those together. Okay, final one. Now I'm going to tell you that this one is a complicated one. I picked one that was more complicated than you will have on your lab. However, you are going to have an organic or hydrocarbon on there with more than one carbon. And so I picked one with 3. I think in your problems, you actually have ones that have 2 carbons in them. So let's go ahead and just do this one. I think you're going to be okay with it. So I've got carbon. It's has 4, but there are 3 of them, so that's a total of 12. And then hydrogen has 1, but you've got 4 of those, so that's a total of 4. So 12 plus 4 is 16. There are 16 electrons. Now carbon here wants to have 8. There are 3 of them, so that's a total of 24. And then hydrogen wants to have 2, not 8. And there are 4 of them, so together that makes 8. So 24 plus 8 is 32. 32 minus 16 gives us a need. Yep, we need to share 16 electrons. So 16 electrons can be divvied out into 8 bonds. Okay, now we did circle the C3, which means there are going to be 3 central atoms in this molecule. And with that, they will each have their own shape. Now, sometimes the shape is identical for all of those central atoms, and sometimes they're different. With this molecule, I've got a clue from the name, and you wouldn't know this. I will give you those clues when I go over how to do the assignment. But when an organic or hydrocarbon ends in -ine, there is going to be a triple bond between a carbon. There's at least one. So I know that as a clue. So if I have a triple bond here and I've got to put 4 hydrogens on this, the maximum I can put here is 1. So this has 2, 4, 6, 8 around it. Carbon number 2 has 2, 4, 6, 8 around it. And so the other 3 hydrogens have to go on the end here. Okay, now let's look at the shapes. So what I'm going to do here, I think I'll use my highlighters to help you guys with this. So with carbon number 1, we've got a single and a triple bond here. And I think that you can recognize from your shapes here that the only one with a triple bond is linear. And so from here to here, with this being the center, carbon number 1 is linear, and our bond angle is 180 degrees. Okay, I hope that makes sense. Now carbon number 2 kind of has the opposite of that, or it's the same, but it's on the other side. So we've got 1, 2, 3, and then we've got the 4th one over here, but it's still a triple bond. So carbon 2 also has a linear shape, and it's 180 degrees. Okay, let's get to the last one, carbon 3. You'll notice that there's no triple bond here. In fact, we've got 1, 2, 3, 4 connections. No lone pairs. Okay, so which one of these has 4 connections? Right here, tetrahedral, no lone pairs. So I would say tetrahedral. And then I would say 109.5 degrees. Okay, so I've actually drawn this correctly. You could go ahead and make this look more like the 3D here. 1, 2, and then this is like the top, and then this is like this. Whoops. This is the one that's kind of shooting to the back. And we've got the tetrahedral. It's easier to see actually if you turn this. So you've got the top here, the 2 to the sides, and the 1 going backward. All right, folks, that is it for our lesson today. Thank you for bearing with. I know it's a long lesson. You will, I promise you, you will get the gist of this. Know that you could come back to this. Know that I'm going to post this page for you guys as a reference, but I also have a typed version that's really nice of this. So I'll post that as well for you. And then when you go on to Molecule Lab B, I am going to just do a quick little intro video for that for you guys. All right, have a great day, everybody. Email us, come to our office hours. We love you and we miss you guys, and we can't wait to see you. I don't know when it's going to be, but we still can't wait to see you. All right, take care.